The marvels of IT. I'll start again. Good afternoon. I'm Erik de Jong from KEMA Labs. I'll be telling you a bit more about what we are doing here, about the testing of the future of EV charging. For me, it is taking the new definitions of the new standard side A. That's the most important part, the grid side. All the problems with side B has been tackled, so I'll be talking more about the side A in here. And especially the high fidelity testing that needs to be ensured as powers go up in EV charging. I'm running through a few topics here, as you can see here, laying down the field, looking at products themselves, looking at systems, and how we can look at testing in particular of systems as we go forward with high power applications. And then there's something called power cybernetics, which has been coined a few years ago, which we want to apply in the EV charging world as well. And I'll quickly run you through that as well. So without further ado, we plug in the battery and start charging. The introduction itself, KEMA Labs. KEMA is a well-known part of Arnhem for more than 100 years already. We are actually 6 kilometers from here, downriver, which is the fastest way of getting between us, although no boat connection yet. Maybe an opportunity for electrical boat service to shuttle us up and down. As you can see, there is our testing facilities, our laboratory complex here in Arnhem. KEMA is part of a bigger Chasey group, multinational. This is our Arnhem campus. We have more in other parts. This is one of the 2 parts where we do tests on electrical vehicle charging equipment. And you see there are also more labs that are more classical and intended for grid components, transmission distribution equipment. So you see a big short circuit laboratory, which Lonneke mentioned is what we are known for, the largest short circuit lab in the world still. There's a high voltage lab for dielectric testing, and then there's the flex power grid lab. That is the lab I am from, and that's the functional testing lab on grid connected equipment, which usually houses power electronics, but we're not a power electronics lab, but we see them quite a bit. And of course, everything that you see here and what we're working with on a day-to-day basis is grid-connected power electronics. So that's our functional testing facility that I will mention to you as well. This is already a picture I've been using a few years, and it's still applicable today. It's from the IEEE. It mentions the ubiquity of power electronics. And what does that mean? It means power electronics is finding its way into all aspects of our electrical and energy power systems, into our lives, our daily lives. Here it shows where power electronics is being used on transmission level, distribution level, household level, consumer level, product level. And of course, what we are talking about here is the AC chargers and, of course, the fast DC chargers with the power electronic conversion happening in them for charging. And at the end of May, we'll be hearing a lot about discharging batteries into the grid or any other application, all done with power electronics. So power electronics itself is an enabler for that. We can't do without, we have to make do with, and they have some characteristics we have to live with. And harmonics is one that always pops up with these type of guys. There's technology advances in that brings us new challenges and shifts us into another domain, like super harmonics. But it also provides us the functionality, the flexibility that we need and we want to do the functions that it's intended for. So we can't do without. And we don't want to do without. We just need to tackle the problems around it. In this landscape, we've been seeing it for fast charging, of course, with the AC charging that we've seen, with just a plug denoting the whole domain. It has come up before as well, the 3 main systems, A, B, and C, for CCS 1 and 2, the CHAdeMO 1, and GBT. And what we are moving towards for the electrification of trucking, transport, larger vehicles is, of course, the MCS. With a, for me, relatively small plug for the powers associated with it. I have had the opportunity of working with one of these, and it is really small, surprisingly small for the power if you know what's behind it and what it's conducting. But that's what we're heading towards for electrification of transport for the trucking sector especially. it's not just that, but we can see a lot of this happening on other levels of grid compliance as well. So we are trying to also bridge the gap with knowledge from other domains, grid-connected applications, generators, requirement for generators on wind, solar, all these type of applications that have been here maybe a bit longer, maybe a few years more matured. Lessons from that applied to this domain. If we look at the product itself, building it from the bottom down, and the more confidence that we have from decades of understanding, testing, and research, we of course start with the AC charging that started off first with testing according to, there we have it, the number soup again, a lot of IEC standards. Well defined, more mature, you know what you get, you know what you're getting yourself into. Here I see the strategy for ALAT as well is our job is almost done with AC. It is known, the challenges can be tackled, it's manageable, let's move on, basically. But just to show you what this means, it's not just electrical testing that we are always, or at least for my domain, talking about the functional parts. There is safety, there is climatic, there is mechanical testing, there's a lot of aspects encompassed in these standards that you also have to take care of. It's not just unlocking the functionality and using the device as is. And this has taken a lot of years to establish, and we are building on that foundation going forward. So with testing for the commercial parties here, the next step is certification. That's a whole different ballgame, and that is where also accreditation comes into play. And for the well-known standards, also our company has the accreditation to do the certification and provide the market with the paperwork you need to get onto the market. So for the AC testing on our sister company in Milan, Chesi company, and here the MID here in the Netherlands with the Raad van Accreditatie being our accredited body here for the MID. These tests themselves, what does that enclose? As mentioned, it's not just electrical testing. So there's climate testing, there's a whole lot of abuse being done on the devices unpowered that it needs to survive. You can imagine what all those tests entail, freezing it, salt, mist, all these things, long duration tests unpowered, which you have to do. There's mechanical tests, ingress protection is one of them. Impact protection, the IK factor is also a very important one, especially if the equipment is out in the public domain. How does it get abused and how can it handle that? So that's also a part that needs to be done. And then mechanical stability is also part of that. Electrical safety, that's the one we usually talk about. How safe is the system when you're close to it, when you're touching it, when you're around it, when you're working with it? How fast is it to be depowered? All these things are unpowered. And then of course the most magical one, the EMC tests around it, where strange things happen and you have to have strange solutions to solve it before things work. Or that's how it's perceived at least. But there's method to that madness, of course. Then there's also the RED directive from the EU that also says that if you put something into the market, you have to comply with the radio emission directive. That also has its own rules and regulations. So this basically sets the scene for the whole lot of standards, directives coming together for something to be tested, certified, at least on the market, and then hopefully work. Apart from that, there's also interesting things that can be done outside of the standards, which ALAT has one part of is the interoperability tests. How do things work together? How do things match up? What can you do with that? Smart charging, an add-on feature onto the device itself. How can that be rolled out? And then some functional testing, usually used for debugging or research on particular aspects of interest that might happen or might not happen that you need to investigate a bit further. So these are also things where a test laboratory such as this and the other competitors come in. If we step up the game to DC fast charging, and I'm talking about the CCS basically up to 350 kilowatts, which is now also enabled here. There you also see the communication interfaces between the car and the EVSE, the EV and the EVSE coming up with, of course, all the standards for those communication protocols, where conformance can also be tested. And these standards come from societies that govern these standards. The well-known one there. Also looking at power quality for the bigger units, as it is not an AC charger anymore. Power is going up, you have a converter connected. You are looking at grid compliance of larger loads, which has some grid compliance requirements as well in terms of power quality and interoperability of the grid. They're also mentioned here. There's also for the higher power units some nuisance measurements that you have to make, noise, light emissions, especially if things are in the public domain or close to residential areas, things you have to take care of. So that's all mentioned there. And here it's above about 350 kilowatts. For DC fast charging, you have to comply with the same RED for radio emission with that directive, so you're not excluded from that either. So you have to take into account all these aspects as well. Then, building up to the next level, it has been mentioned here as well, the megawatt charging system. This is when things become really interesting. For me, bigger, higher power is still better. Where now the confidence level is also decreasing from the AC where we know everything, the DC where we're getting grips on what's happening with megawatt. We are still, I would say, in infancy. There's the organization looking at defining the standards for communication, the MCS standard, who brought out a white paper with all these normative references in there that should be included in the standard that should come out, but it's not here yet. So there's a lot of formative discussions now getting into what will be the megawatt charging system. You can see a photo of the plug on your right-hand side and a long list of standards which will be incorporated in some way or another into this MCS system. So that's what is ahead of us. If we look at, we go from products and we go to system requirements and we look back to the MCS, you see the same plug here. You now see that we are now handling possibly theoretical powers of up to 3.75 megawatts, 3000 amps DC, 1500 volts has been mentioned as a safe low voltage value. These are considerable amounts and deem respect from these components. And of course, the idea behind the MCS, or one driver behind it, is to be able to respect drivers' drive and rest times with electrical infrastructure, giving them the opportunity to rest and charge their truck in the same time, which means bigger batteries need to be charged in less than 45 minutes. And that's where you end up with currents exceeding 1000, 1500 amps to be able to charge the batteries within coffee drinking and bathroom break time. So the drivers are there, the motivators are there. Now the technology should support that. And of course, it should be grid connected, and from the energy point of view, should be able to handle that as well. Not just one charging station, but you can imagine if there is a truck stop, it's not just one truck stopping at the same time. For anybody who has traveled through Germany on leisure or business travel, if you are at the truck stop, there's many at the same time. And if this is the future, then there's a huge challenge for the side A part, grid-connected side. So that brings us from what have we done before, which has been focused on component testing, where we have standards that are there, clear, harmonized or not, but are being used, where we can do testing in facilities like this, with or not certification behind it, to show that it complies to a standard. And that's great, and we should be keeping on doing that, because that gives the quality of the product that you have into the market. But with these bigger systems, the risk is that that's not enough. And when you look at what needs to be done, is that this needs to be included into a system level testing, where not just one product is in the system, especially looking from a grid point of view, but multiple systems work together and need to be able to work together. So you have to do system level testing to show interaction between similar units, different units, not just interoperability from the user point of view, but from a grid point of view. Can it be sustained? Can it do everything it needs? It takes a different approach. You can't just base it on the individual product or component standards anymore, but you have to consolidate that, do system level testing, higher level of testing, but if you do that correctly, you can say that it's fit for purpose, which is a very specific requirement instead of a general requirement coming from general standards. And I think that's the message that I want to say here as well. As we grow up in numbers and in power, the focus is not just on the product testing anymore, but needs another layer of activity as well to get the quality and the usability and availability, what Lonneke also started with today, from our infrastructure, basically. What does that mean for laboratory infrastructure? We have a facility here that can do parts of that. We have our facilities in Arnhem. The DECRA has facilities here in Arnhem as well. That can be done. The one I know the most about is the one that I run, so that's the Flex Power Grid Lab, which is our test bench for these type of activities. It has grown out of the grid compliance testing of grid-connected or utility interactive power electronics world, where this is now also entering and combining. So what we have there is a megawatt scale laboratory with some tools to be able to create the boundary conditions to do product testing, but also allows you to do the system level testing and interact with multiple applications. So what you see there is a very small version of a single line with all the tools and the gadgets that we have. What we have in there just on a high level is the high voltage, high power AC grid simulator, building block, one of the puzzle pieces to emulate the AC grid you're connected to, give you the fidelity, the high fidelity that you need on the AC side. We also have, since the opening here, updated our system with low voltage but higher bandwidth amplifiers, and that will get us into the next chapter, which I will tell you about, where you go from the 2-3 kilohertz bandwidth amplifiers to 10, 15, 25 kilohertz, adjusting with the requirements and the technology increase from products. On the DC side, we also have the same environment, as you can see there, more than 1 megawatt bidirectional DC supply that you can use initially as a PV emulator here, but with full VI characteristic curves and being bidirectional. It can also be a battery emulator, which we have done already. So that is the other end of the charger on side B. You have to give the charger opportunity to charge into something that's hopefully not a battery, because for testing batteries are time intensive and needs to be discharged. So an active bidirectional load is preferred to reduce testing times. And for some aspects, you just have to take care that an active source and an active charger working together do not interfere with each other enough to void the test results. That's where the experience from the test laboratory comes in, to know when to apply a tool and when not. But these are the power levels that we have available, and as you can see from the MCS growth that can be foreseen, it's too small already. And that is what brings us to how do you keep up with accelerated market trends in an asset-heavy environment without building a new lab or building bigger, bigger, bigger every time and always looking behind. And that is what brought us to believe that instead of going bigger, bigger, and bigger, go smarter and then have the tools to facilitate the smarter approach of testing. We call it power cybernetics, and the idea is simple. Emulate what you can without avoiding or nullifying the results of a test. So what we embrace here is hardware in the loop, power hardware in the loop, with real equipment in the middle, and emulating all the boundary conditions as far as you can with the high fidelity signals that they require, so that you can draw conclusions from the results, the interactions, and the aspects that you are testing. Here you can see a grid view of how that could be, where you have equipment under test and all the boundary conditions, also from communication to backends, all these aspects are connected to it and communicate in its own time domain the correct values to give it the correct impulses it needs to excite a certain working point and condition for testing. This, of course, can easily be applied, reapplied for the EV charging, the DC fast charging situation as well, emulating the DC side, emulating the AC side, and if you're in a climate chamber, at the same time also influencing the climatic conditions around such a device. It gives you multiple levels of freedom that you can use, but also the opportunity to get the device that you're testing in unique operating points. And for climate chamber, it's not that fast, but you can imagine for electrical interfaces, the bandwidth will just increase as switching frequencies and functionality of the devices increase. And you have to stay ahead of what you are testing, of course. So that's the idea of power cybernetics that we are trying to embrace here for what we see as the future of EV testing. To give you some insights into that, the hardware in the loop, for those that do not know the concept, is quite easy to understand. You have a real world component, you have a virtual component that's modeled, and you have to connect the two together. And it sounds easy, but that's where the complicated part is, how to make things believe that they're connected to something that doesn't exist. But if you can do that correctly and nicely, then you have a tool that gives you more reach than a standard dedicated test facility would. And that gives you the key to do more with limited amount of resources, space, area, and budget, of course. So that is for me. You can see the battery's been charged in this session alone. Just a few more minutes to draw some conclusions on here and perhaps pose the last question. So you can see that I tried to convey the message that product compliance to standards is still important and will be important and should still be done. But we have to think for the next step as well on system level testing to show fit for purpose. And the more detailed you can do with the purpose, the more dedicated models you have that you can put into a hardware in the loop situation, the more confidence you can entrust onto the results that you get from such a system of that. We think power cybernetics is the future for tackling this ever-growing problem that's hitting us, to keep the market alive, to keep the quality in the products, and in the end also do certification based on something like this, although that is still a bit further on. And for now we see MCS popping up. I saw the ELA timeline 2025, 2026. I hope we can make major steps in that. But my question for test facility, of course, is what's next? Because that's what we have to prepare for now to tackle and be ready for those challenges in the market. And with that, I conclude my presentation now. Thank you.